Today I want to present a new feature in the Spectra package, which is the ability to generate annotated chromatograms. So let me start by illustrating what an annotated chromatogram is. So those familiar with mass spectrometry would immediately recognize a chromatogram here, where we have for the MS1 events in this experiment on the y-axis the total ion current, the total signal that was recorded for these, along the experiment's retention time. In addition to that, on this figure, we have the individual MS1 events that are highlighted by dots. And these dots are either gray, like those here at the beginning, because these MS1 scans did not have any precursor ions that led to an identification. And the other dots here that are color-coded from dark gray or dark blue to light blue are these MS1 scans that led to either one or, in one case, up to 10 precursors leading to identifications. And so this figure is, I believe, a really nice quality control that illustrates the current, the signal that was recorded, but also gives you an idea about how many identifications were produced based on this acquired signal. So I'd like to walk you through a little code snippet that illustrates how to generate these annotated chromatograms. And so the data that I'm going to use to illustrate this comes from the MS data package. And so here I have a raw data file, TMT Arinia, and its associated identification file as an MZID file. So we have these raw data, an MZML file, and the PSM data, an MZID file, and the very first thing that we're going to do is to load the Spectra package and then import this raw data as a Spectra object and store this data into a variable called RW. And as we can see here, this data is composed of 7,534 spectra, MS1 and MS2 spectra, of course. And we're going to do the equivalent for the identification data using the PSMatch package. And here I'm going to load and to filter these PSMs. And as we can see here, we have 2,666 PSMs, 264 unique peptides, and we only kept those of rank 1 and removed the decoy hits. And the next thing we need to do is to combine these raw data stored here in the RW variable and the identification data. And here we specify that we need to combine these based on the spectrum identifier. And we're going to ignore the warning here. If you're interested in this, please have a look at the Spectra documentation or the mass spectrometry tutorial that I will highlight later on. So running this join Spectra data function, we add a new variable, the sequence variable, to our raw data. And of course, many of these elements, sequence elements, will be NA because there was no identification, but in some cases we do have peptide sequences. And so the next thing that we want to do is now to run this new function called count identifications using passing the raw data object as input. And so this function will look for a sequence variable in this raw data object, and it's going to count how many identifications we have for each spectrum. So this is pretty straightforward for MS2 scans, because either we do have an identification, for example this one, and then we count 1, or we don't, the sequence variable is then missing, and then we count 0. For the MS1 scans, what's going to happen is that the function is going to look at all the MS2 scans that were produced based on precursor ions from each of these MS1 scans, and then count among, in this case it's always 10 MS2 scans, how many of these produce an identification, and then tally this count and associate it to that MS1 scan. So this count identifications functions will create a new variable in our raw data object called count identifications. And so let's have a quick look at what this function produces. And let's look at the content of these count identifications for MS1 and MS2 scans. Now, as you might expect, for MS2 scans, we have either 0 or 1 counts. There is no MS2 scan that has more than one identification. And we have 3,457 MS2 scans that didn't lead to any identification, and 2,646 that did lead to an identification. That's quite straightforward. If we now focus on the first row here for the MS1 events, we have 833 MS1 scans for which none of the precursor ions led to an identification. We have 30 MS1 scans for which we have a single precursor ion that led to an identification, 45 that led to 2 identification, 97 to 3, and so on. And we even have one MS1 acquisition here for which we have 10 identifications. If we now look at all the variables that we have in our raw data, we have the retention time here. We have the total ion current here. So these are the variables that we need to produce our chromatogram. And we also have here the count identification. So this tally of identifications for each MS1 scans. And with these data, we can produce the figure that we want. So let's start by loading the tidyverse, because we will need the ggplot function to produce the figure. So here I have my raw data set. I first filter only MS1 level data. I'm not interested in the MS2 scans here to produce my figure. I extract that data frame that contains the retention time, total ion current, and the number of identifications. I convert it to a table, and then I use ggplot2 to produce the figure that I'm interested in, that as I explained at the very beginning. So if you would like to have more information or have access to the code that I just briefly illustrated, have a look at my GitHub page. And if you want to know more about the count identifications functions or the Spectra package in general, have a look at the Spectra package webpage or at the alpha mass spectrometry tutorial where you'll be able to find lots of additional features to analyze raw mass spectrometry data and identification data. Thank you very much for listening.